Okay, hi guys, welcome back. We last discussed our first example of normed linear spaces, namely the continuous functions on intervals 0 to 1. We defined, well, a few objects on them. Those will be norms, but right now actually we can't use that word for it yet. There's on one hand the infinity one, as written down there, which is just maximum of the complex modulus of the function. Then the other one are the integrals for finite p from 1 up to infinity. We argued that these objects are positive definite and homogeneous, and now it requires to establish the triangle inequalities. Triangle inequality I showed here for p equal to infinity. I said for p equals 1, this is also easy because you use the properties of the integral up there. And for p equal to 2, I gave an argument using some knowledge about inner products. If that argument, by the way, is not known, you don't need to worry because p equals 1 and p equals 2 will be contained in the upcoming two results. Okay, so to prove the outstanding triangle inequality, we first need a little helper, which is actually a very famous helper, which is the Hölder inequality. Okay, so the statement is written here. You start with three numbers, p, q, and r, from 1 up to, could be equal to plus infinity, such that, and that is a very important condition, the quantities 1 over p and 1 over q, they sum up to 1 over r. All right, so if, for instance, r is equal to infinity, then the right-hand side in that equality would be 1 over infinity, I interpret as 0, and that means then in turn that both p and q also have to be equal to infinity. Okay, now what's the actual statement then? Given two continuous functions, the product is continuous. Well, that doesn't require any further explanation. This is a fact of real analysis. And then what needs explanation is we have the following inequality for the product. Okay, so the product fg in R norm cannot exceed the product of the individual norms, but the first one in P and the second one in Q norm. Okay, so this is the famous Hölder inequality. Once we have it, then we'll be able to prove the triangle inequality that we need. Okay, so let's get started. First off, the case P equals Q equals R equals infinity is obvious. Why is this? Well, so then there are also primums norms, and of course if you have product of two functions, the complex modulus is multiplicative, so you can split it here with one as a product of two complex moduli, and then you optimize, not in blue, not in yellow, but in blue, you optimize both of them. Then you get immediately f infinity and g infinity, and since this holds for all x in the unit interval, you just optimize the left-hand side, and you indeed get this inequality for p equals q equals r equals infinity. Okay, so this requires no further explanation. Now, moving ahead, we also can assume that the functions are not identically zero. Because if at least one of them is identically 0, say f, then of course the left-hand side here will be 0, and so will be the right-hand side, and 0 is clearly less than or equal to 0. So that also requires no further comment. So we can assume they're not identically 0. Okay, now by considering the statement why I don't want to deal with the functions identically 0 plays a role in the following line. By considering function f hat, which is just f in complex modulus to the power r, and then I want to divide by this norm, and that's why I don't want it to be 0. This is the p norm raised to the power r, and g hat, which is function complex modulus of g to the power r, and then g q norm to the power r, we find with say p hat, which is p over r, and q hat, which is q over r, that Well, the f infinity p hat norm. Okay, so the p and the p hat and the q hat are not going to be infinity, so these are all going to be integrals. So now if you stick this in, let's do one maybe, you know, explicit. So 0, 1 f hat x to the power p hat dx to the power 1 over p hat. And now you recall what the definitions are here. So p hat is p over r. So you have 0, 1. And then what is f hat? Well, f hat is written up there. So this is f of x to the power r p norm of f raised to the power r. And then I need to raise this to the power p hat, which is p over r. And then I have 1 over p hat. Okay, let's leave this as is. Now you can see here inside the r powers, they go out with the rth root. And then you can pull out the scalar, well, outside, but you have to be careful with the powers. So inside I have 0, 1 f of x to the power p. Here I'm missing also dx, okay. And now I have this here to the power 1 over p hat. So this is r to the power p. And what do I get outside? I have 1 over p norm to the power p, and then divided by p hat. Okay, so p over p hat is just r. So what I have here is 1 over f p raised to the power r. And now what is written here in the bracket? Well, this is exactly by definition the p-th norm of f raised to the power r, right? So you see you have the same object here, so they cancel out. So this is precisely equal to 1. Right, so this is sort of a rescaling trick, and you can do the same argument for q, for g with the q. You will find the same answer. Similarly, g hat q hat is equal to 1, and when you sum up 1 over p hat plus 1 over q hat, because 1 over p plus 1 over q is 1 over r, this is exactly equal to 1, right? So in other words, by using this little rescaling trick up here, you can reduce the general Hölder inequality to the special case where your function has, well, p hat norm equal to 1, q hat norm equal to 1, and 1 over p hat plus 1 over q hat is equal to 1. Okay, let's write this down. We are thus reduced to the special case f p norm equals g q norm, just relabel the hat quantities without the hats, and 1 over p plus 1 over q is equal to 1. Okay, so that makes it a little bit easier. Okay, but now we need a tool that you guys will actually investigate in the exercises. This is Young's inequality. This is something that you can prove in calculus. Young's inequality is x of y is less than or equal to x over p plus y over q whenever x, y non-negative and 1 over p plus 1 over q is equal to 1, with 1 p q less than infinity, so they have to stay away from 1. We find for all x in 0, 1. So what you're going to do is you're going to use this general inequality here, and you're going to replace x by complex modulus of f of x and y by complex modulus of g of x. These are non-negative real numbers, and then you continue and get your result. Okay, so let's write it down. We have f of x, g of x less than or equal to 1 over p f of x to the power p plus 1 over q g of x to the power q. This is Young, and all that you have to do is now integrate both sides from x equals 0 to x equals 1. This yields at once, because remember f and p, they're normalized to 1, so their p norms and their q norms are equal to 1 after integration, and this will just become 1 over p plus 1 over q, but those indices, they sum up to 1. Okay, so you find immediately that the 1 norm is less than or equal to 1, which is f of p g of q. Okay, and that's it. That completes the proof of Hölder's inequality. Okay, good. It's quite cute. This inequality is immensely powerful. Okay, we will have various different versions of Hölder's inequality appearing very soon. Okay, good. But now let's use it. So we want to show the triangle inequality for our norms on C01. Okay, so that triangle inequality actually has a name by itself. It is the Minkowski inequality. There's different ways of proving it. One way that I'm presenting here goes through the Hölder inequality. So here we go. Let 1 less than or equal to p less than or equal to infinity and f, g be continuous functions on 0, 1. Then again, fact of calculus or real analysis is that if you take two continuous functions and you add them together, you get a new function, and that thing is also continuous on the same interval. More importantly for us, we have indeed the triangle inequality that we like. P norm of f plus g cannot exceed the sum of the individual p norms. Okay, that's it. That will be the triangle inequality. Okay, let's prove it. We may assume 1 less than p less than infinity. This is because when p is equal to infinity, I already proved the Minkowski inequality earlier in yellow, and when p is equal to 1, this is just properties of the integral and the ordinary triangle inequality. Okay, so now let's start working. Since I don't want to carry around the pth roots, so I will raise the p norm to the power p. So this is by definition, here for p away from infinity, this is the integral 1 over p f of x plus g of x to the power p dx. Okay, now a little bit trickery here allows you to write this as f of x plus g of x p minus 1 f of x plus g of x dx. Okay, so now here we use that p is different from 1 because that means that this exponent here is strictly positive. Okay, now what you do here is you're going to use the ordinary triangle inequality for the complex modulus. Okay, and then you use the integral respects that inequality. Okay, so this is going to be less than or equal. I can split it into two parts. First part, fx plus g of x, p to the minus 1, I'm not going to touch this, and then f of x dx, and then second integral 0, 1, f of x plus g of x, p minus 1, g of x dx. Okay, so now what we're going to do is now we're going to use Hölder inequality. So let me write Hölder here. So I have to relabel my functions. So Hölder inequality for r equals to 1 is this statement p gq, where 1 over p plus 1 over q is equal to 1. This is Hölder's inequality. So now what you have to do is you have to identify what is the capital F and what is the capital G. Okay, so I will do it. So we will take this here as capital F and this guy here as capital G. Okay, a similar thing in the second integral here. You take the little g as your capital F and you identify it with capital F, and that fx plus g to the power p minus 1 as capital G. Okay, so once you do this, what do you get by applying Hölder's inequality? Well, it's written here with p and q, so I will have the p norm of small f. Okay, so let's write this out. This is the p norm of small f, and then the q norm of that remaining piece. So what was the remaining piece? This was f plus g, and then there was the exponent p minus 1. Now in the q norm I have to raise this to the power q. So the rules of exponents tell me this will be to the power q p minus 1, and then qth root of that. Okay, let's write it a little bit nicer here. Plus, and then for the other one you do the similar thing. So you have g of p and 0, 1 f of x plus g of x q p minus 1 to the power 1 over q. Okay, but now a little algebra reveals that these two guys, which are the same, are actually equal to p. This is because 1 over p plus 1 over q is equal to 1. Just stick that equation in there, you get that one. Okay, so what you have here now it's an equality. You have f of p plus g of p, and then the common factor is 0, 1 f of x plus g of x to the power p dx to the qth root. Yeah, but this is f of p plus g of p, and now what is written here, this is the pth root to the power p over q. Okay, you can check. All right, so what you have now all together, you started on the left with f plus g to the power p. It is less than or equal to f p plus gp. And now this quantity f gp to the power pq. Okay, what you do is you combine these two terms, you bring this to the left, then the exponents become p and 1 minus 1 over q, because you have to divide, right? You have to divide this to get it to the left. Yeah, but this is precisely 1. Okay, so then you indeed have what you want, that the pth norm of f plus g is at most the sum of the individual p norms. Okay, and that completes the proof of Minkowski's inequality, and hence the triangle inequality for the norms on C01. And now we know that indeed, equipped with those guys, C01 is a non-linear space. Okay, good. Let's go straight to the next example, which is sort of the discrete version of all of this. This will also be very useful, will appear frequently. These are sequence spaces. So let X be a sequence we introduce in the vector space. That's usually something that you don't talk about in linear algebra. The continuous functions or polynomials actually they appear in linear algebra. So that space is probably known. Now we turned it into a normed linear space, but this one here, vector space of all bounded sequences, that's typically not discussed in that module. This gets a special symbol. This will be L infinity and then n. So these are all sequences, well, which are bounded. That is to say, the supremum over all terms is finite. Okay, so this is in a sense the discrete analog of the space that we had earlier, continuous functions. Well, on a compact interval, they're always bounded, right? So in a sense, this mimics that. Here now, we don't have a variable x, which ranges continuously from 0 to 1, but we have the index small n, right, which goes from one integer to the other. That's why sort of discrete analog. Okay, so we have the bounded sequences, and in the vector space of all p-summable sequences, right? So this is really the discrete analog earlier of these integrals. Well, there you don't have to introduce new spaces because continuous functions are integrable, but here it's slightly different. So there we look at the ones where xn raised to the power p and then sum out all the n's is finite. And again, p at least 1, but staying away from infinity. Now, it turns out both of these guys, these are very important, this one and this one, they are normed linear spaces, and I will define two objects now that will turn out to be norms. Okay, both spaces are normed linear spaces with the following norms. In the case of the bounded sequences, the standard norm will be, well, the infinity norm again, which is the supremum over all x, and this is finite by definition of the space because the space only contains those objects for which that thing is finite. And in LPN we will look at the p norm, which is, so this is definition, which is just, well, the discrete analog of the integral, which is a sum. So xn to the power p and then 1 over p through. So this is for 1 to infinity. Okay. Just as in the previous example, it's easy to see that both these guys are positive definite and homogeneous. Proof is almost the same, just replace the integral by a sum. Again, triangle inequality requires some more work, but we will just summarize this in a theorem. This is again a Hölder-Minkowski inequality, but here now in the discrete version. So let me just write discrete Hölder and Minkowski inequality. Here's the statement. Let first Hölder, let 1 PQR between 1 and infinity with, I mean, the statement reads exactly the same as in the previous theorem on Hölder's and Minkowski's inequality, but okay, the objects are different. These are not functions, those are sequences now. So if x is a sequence in LP and y is a sequence in LQ, then the product is in LR. So this is not as obvious as the previous statement that if you have two continuous functions, the product is continuous. Here this requires some work, but nevertheless it is a consequence of Hölder's inequality after all. XP YQ, right? So once you have this inequality, and if x is in LP, then this is finite. If y is in LQ, this is finite. So the product will be finite, hence the left-hand side is finite, and that precisely tells you what's written up there. Okay, this is Hölder and the Minkowski inequality. Similarly, furthermore, if 1 less than p less than infinity and x, y in LPN, then their sum is in LPN. That's easy to see. The sum is very easy, much easier than the product. And we have Minkowski inequality p less than or equal to xp plus yp. Okay, that's the statement. As far as the proof is concerned, I actually won't prove it because it's exactly the same as in the previous world with C01. The only difference is you have to replace integrals and continuous variables x by sums and discrete, well, summation variables small n. Okay, so we'll just write as in the previous continuous versions and nothing else. Okay, this requires no further comment. Okay, all right, so we have now these two very important examples. We got function spaces, continuous functions on 0, 1. We have to find norms on those, and we have the sequence spaces, bounded sequences, and p-summable sequences, again equipped with norms. These are really very important examples. You should familiarize yourself with those. They will appear frequently as our toy examples when we have developed more theory and we want to apply that. Okay, see you in the next video.